Good news everyone, we've made it to group 18. So this is the last video that will be looking at an individual group. The next video will just be a summary of the chemistry that we've seen throughout all the groups and what's really important. Now I've been bashing group 18 through the whole course up to this point, saying that this is a bit boring, they don't really do anything and there's not much chemistry. So in this lecture I'll show you that I'm wrong. There are some reactions, they do make some compounds, and it is actually quite interesting. But there isn't that much of it, so it's still going to be quite a short video. Although, yeah, as I say, the chemistry of it is quite interesting because up until recently, no one thought any of it was possible. Now, group 18, also called the noble gases or the inert gases, right on the right-hand side of the periodic table, and they've got this valence shell electronic structure of ns2-mp6. So they've got a full 8 electrons in their outer shell, and that's why everyone thought for millennia that they were completely inert. That's why they were called the inert gases, and that they would do nothing. So we've got 6 of them: helium, neon, argon, krypton, xenon and radon, and they're all colourless monoatomic gases, so in general unreactive. Radon's very interesting in that it is also a colourless monoatomic gas, but it is radioactive as well. But that's about as far as we'll talk about radon. Now they're all present in some extent in the atmosphere, so you can actually do fractional distillation of air. So I don't know if you did about fractional distillation when it came to crude oil refining and getting hydrocarbons, but you can do the same thing with air. So it's essentially just cooling it down to different temperatures, and then each of the gases will liquefy and be taken out at a certain temperature. And helium has the lowest of these temperatures, so it liquefies at -269 degrees C, which is very close to absolute zero. It is the lowest boiling point of any element. And what's quite interesting, or two things that are quite interesting: at atmospheric pressure, helium's the only element that won't actually solidify, so you can cool it down all the way to absolute zero, which for reference is at -273 C. So you can see it's very close to as cold as is humanly possible, or physically possible. Even at -273, it won't become solid. And there are actually like 2 liquid phases of helium. So it liquefies at -269, and then a couple of degrees lower, so I think it's around -271, it becomes a superfluid, which are described in this video. But essentially it's a liquid where the viscosity is 0. So, and then they get really weird properties. So things like if you stir a cup of tea and you make that vortex, usually you stir it, you get this vortex, you take the spoon out, a couple of seconds later it stops spinning. This one, if you had a teacup full of superfluid helium and stirred that and got this vortex going, this sort of whirlpool, it will whirlpool forever. Like, it doesn't lose kinetic energy. So very bizarre. It's quite hard to get your head around. Now the inert gases, they do have their uses even though they're not inert. So helium we use for balloons, make them float. Neon and argon are used in signage. So neon signs are actually using neon. They were named for a very obvious reason. Krypton and xenon are also used for lighting, and this is more commercial applications such as on runways. So it's mainly like playing with the gases to get emission. And then, as I said, radon's just a radioactive gas. There isn't so much more to say about. But they can actually make compounds, or at least some of them can make compounds, and that's what we're going to look at on this slide. Literally just this slide. As I said, there isn't so much chemistry with them, and although it's interesting, there isn't much, so there's not much to talk about. But this all stems from the high enthalpy changes of ionization. So that's the step in the Born-Haber cycle. The other way we'd think of it is the ionization energy. So they've got really high ionization energies because they've got this full valence shell, which makes them very stable. But as we've seen with ionization energy, it decreases as we go down the group, or decreases with the increasing size of the atom. And this means that at the top of the group, where we've got helium and neon, we don't have any chemistry of these. Not a single compound is known of helium and neon. Argon, further down, there's a total of 1, This one was first synthesized in 2000, so it's like, yeah, barely 20 years since we've had a compound of argon. And at least when the textbook was written, there is still just this one, and it's not very stable. It's only stable below minus 246 degrees. So yeah, there's one, and it's not too easy to get. Krypton has a few more, so I'm not going to put numbers on it now. Krypton has a few more as it goes down. It's got this lower ionization energy, and it can make quite a lot of fluorides. But xenon is the one we're going to really be focusing on because it has the most extensive chemistry. Because of it's right near the bottom, it's got the lowest ionization energy of them all, so it can bond with more things, mainly fluorine and oxygen, and this is because these are the most electronegative. So yeah, combining a high electronegativity with something with a relatively low ionization energy means that chemistry is possible. So we'll start by looking at the fluorides. These are the first ones that were discovered. And when they were first discovered, it was actually as a complex, like a xenon fluoride with, or an ionic one even, xenon fluoride with platinum fluoride as well, like two of them together. But yeah, we can get these three xenon fluorides, so the difluoride, tetrafluoride, and hexafluoride. And these first two go nicely with how we'd expect them to be through VSEPR. With a linear and a tetrahedral shape. But this one, the hexafluoride, doesn't behave quite so nicely. We'd expect it to have an octahedron with a xenon in the middle and then fluorides making a square in the middle and up and below. Draw that quickly. However, it's actually like a distorted octahedron, so it still makes this general shape, but instead of them being very uniform bond angles, what we'd actually see is like one of these fluorides then would be off at a bit of a funny angle, and this is because there's a lone pair on the xenon that has to fit somewhere, so it fits in between the faces of this octahedron, but it can move around, so it's not like it always has this one slightly distorted funny bond. This could be any of them because as this lone pair like whizzes around between any gap it can find. So yeah, we've got three fluorides of xenon. Which of them form depends on some reaction conditions like the temperature, pressure, stoichiometry, and they're all strong fluorinating agents. So they'll act as both fluoride ion donors and acceptors. And we've got an example here of a reaction with a fluoride ion acceptor. So it's acting as a donor in this example. And it's the arsenic pentafluoride we saw in the last video on the interhalogens as well, where it takes a fluoride ion, so we can end up with a xenon fluoride cation. And if you chose a suitable fluoride ion donor, you can also end up with the xenon fluoride anions. Finally, let's look at some xenon oxides, or one of them. These are made by taking a xenon fluoride and hydrolyzing it with water. So then the fluorine or the fluoride is replaced by the oxide ions, anions, and we also get some just atomic xenon gas given off because it's super stable as it is, so it quite likes to just get made. And then our old favourite HF. And this is another example of a disproportionation reaction, like we saw in the S-block chemistry with the potassium superoxide, where that can break down to oxygens of different oxidation states. That also happens with this xenon tetrafluoride. So the oxidation state here is +4, and then it goes to +6 in the oxide, but then also 0 with the elemental xenon. So this is another good example of a disproportionation reaction. And I'll just finish up this slide in this video with a little bit of history in the future on these. So the first, all of this chemistry has been discovered in the last, say, 60 years. So the first xenon compound, that one I was saying was like a xenon with a platinum fluoride as well. That was first discovered in 1962. So it's only been 60 years of research finding out all of this. And as research has gone on, especially in the last 20 years, it's picked up. They've also found xenon compounds making compounds with chlorine and stuff as well. So it's very young, but it is expanding.